Yesterday, we ran the long test on the longbow sensor. From mid-afternoon all the way through the next morning, we were looking at something called kurtosis, basically a math tool that tells us how stable a light beam is. If the beam is steady, kurtosis is low. If the beam is jumping around because it's hitting something, kurtosis spikes. We started at 2:38 p.m. and the air was dry and clear. Because we're now sampling 600 data points instead of just 100, the baseline was rock solid. No jitter, no noise. The math was perfectly quiet because there was nothing in the air to disturb the light. Fast forward 7:22 p.m., the humidity hit 100% RH. Usually you'd think that's when the fog starts, but the sensor showed that something different. Even at 100% RH, the kurtosis stayed flat. The air was full of water vapor, but the vapor was still invisible. The beam was passing through it like it wasn't even there. Then at 8:38 p.m., we hit the tipping point. The temperature dropped below 50 degrees Fahrenheit. Cold air can't hold as much moisture as warm air, so that invisible vapor finally had a turn into physical droplets. The discovery. This is where it gets interesting. The moment we crossed 50 degrees Fahrenheit, the kurtosis exploded. We saw a lightning bolt of data. The wavelength kurtosis shot up over 5,600. The sensor wasn't just seeing darkness, it was seeing the physical birth of fog. By using 600 data points, we caught the exact time the air transitioned from gas to liquid suspension. This is what demonstrates that this isn't just a smoke sensor, it's a high-resolution weather monitor. We can now use light to fingerprint the exact moment of fog formation in real time. It's a major scientific finding, and the data is clear as a bell. How a light beam reacts to fog formation. When you are above 50 F and 100% humidity, you likely have high humidity but clear air. Once you drop below 50 F, the air reaches a tipping point, creating a suspension of microdroplets. These droplets are large enough to interfere with the longbow beam. The kurtosis spike indicates that the 600-point sample is no longer a standard distribution of light readings. It is being hit by intermittent extreme scattering events, the droplets passing through. This isn't just noise, it's a physical record of fog or heavy dew formation physically entering the optical path. Moving from 100 to 600 data points for kurtosis is about getting a confident signal instead of a nervous one. Kurtosis is a fourth moment calculation, meaning it takes the noise and raises it to the power of 4. Because of that math, a tiny bit of electrical noise or a single dust flake on a 100-point sample can cause a massive fake spike. It's hard to tell if you're looking at a real weather event or just a math fluke. By using 600 points, you are getting better information for 3 reasons. Baseline stability. In the afternoon before 7 p.m., their kurtosis stayed very flat. With only 100 points, that line would be chattering up and down, making it harder to see that the fog actually starts. Outlier confirmation. When the temperature hits 50 F and the kurtosis spiked to 78 and 600 point, providing it wasn't just one lucky droplet. It was sustained change in the light's behavior. Signal to noise ratio. The 600 point filter out background hum of the sensor. It allows the physical signal, the fog droplets scattering the beam, to stand out clearly against the math noise. While lux kurtosis monitors the stability of light intensity, wavelength kurtosis provides a unique diagnostic layer by tracking the spectral purity of the beam in clear air. The center wavelength remains highly consistent, but as the condensation forms, the physical properties of water droplets create wavelength-dependent scattering. Because wavelength kurtosis is sensitive to these shifts across the 600-point sample, it can flag atmospheric changes even when the total light level lux appears relatively stable. Having both metrics allows the system to distinguish between a simple obstruction, which might only affect intensity, and a true metallurgical event like fog or haze, which distributes the light's special distribution. This dual-layer approach significantly reduces false positives and provides a much more detailed fingerprint of the air quality between the light source and the sensor along the 3-meter light path. The longbow sensor effectively functions as an open-air laboratory, using the light beam to detect atmospheric transitions that standard weather stations might miss. By monitoring the statistical distribution of lux and wavelength over 600 data points, the system can distinguish between simple high humidity and physical onset of fog. The data from the last run clearly demonstrated this capability, identifying a precise phase transition when cooling below 50 F in 100 RH conditions triggered significant scattering. This high-resolution approach turns a simple light path into a sophisticated tool for real-time visibility and condensation monitoring. It is exciting to see how these kurtosis calculations provide clear mathematical fingerprint for environmental changes, providing that your wood stove automation technology has a powerful secondary application in meteorology.